Imagine 2 laps through the same corner, same car, same tires, same driver, and even the same entry speed. But on one lap, the car refuses to rotate, and on the next lap, the car rotates and points cleanly towards the apex. The difference might not be because of the steering angle, but rather what happened on the brake pedal half a second earlier. This is what the load transfer does. The driver feels it as understeer, oversteer, traction, rotation, instability of the vehicle. But underneath all of that, what the car is doing is adjusting all of its load and distributing it across the 4 tires. The tricky part here is that adding load to a tire increases its force capacity, but it does not give the whole car free grip. In fact, too much load transfer can reduce the total available grip from an axle. And I'll be using this AI generated simulation to explain the load transfer more effectively in this video. The phrase everyone uses is weight transfer, but the more precise phrase is load transfer. The car's mass has not physically moved forward while braking or jumped towards the outside while cornering, but rather what changes is the vertical force on each tire. Engineers usually call this as normal load or the FZ. At rest, the front and rear tire loads come from the static weight distribution. If the center of gravity is closer to the front axle, the front tires carry more static load, and if it's closer to the rear axle, the rear tires carry more loads. But when the car accelerates, brakes, or corners, the tire contact patches apply these loads at the road level, but the car's inertia is acting to the center of gravity, which is above the ground, which introduces pitch and roll movements. The vertical loads on each tire redistributes to balance these movements. And that redistribution is exactly what the driver feels. Under braking, the load transfers forward, which means the front tires are carrying more normal load compared to the rear. That is why the front axle usually has more braking capacity during hard braking, and it is one of the reasons that the front brakes are much bigger in size and much more thermally loaded. Under acceleration, the load transfers backward. In the rear wheel drive car, this could actually help the rear axle to put more force to the ground, which means you get better drive and better traction. But in a front wheel drive car, this could hurt the traction because the driven axle is actually getting unloaded during the acceleration as the driver asks for more. This is where the pitch moment comes in. And anti-dive and anti-squat geometries can change how these movements are reacted by the suspension links versus the springs. But the basic longitudinal load transfer demand can still come from the CG height, the longitudinal acceleration that you're experiencing, and the wheelbase, which is the length between the front and rear tires. During cornering, the load transfers laterally, which is why the inside tires are losing the vertical load and the outside tires are gaining more vertical load in this case. This is why the cornering photos sometimes look dramatic, where the outside suspension compresses and the inside starts to lift off the ground. And in an extreme case, given the lateral acceleration is too much and the center of gravity is much higher relative to the track width, the car can sometimes roll over. For performance car, the usual goal is to keep this CG as low as possible and keep the track width as high as possible, which is why you would usually see the race cars having wide body kits and are very low to the ground. This reduces the load transfer and makes sure that the loads are distributed evenly across all 4 tires, even during turning. But the interesting part for vehicle handling is not only how much load transfer happens, but where it happens relative to the front or rear axle. If there's too much load transfer at the front axle, the car understeers. The driver is asking more grip from the tires than they can provide at that point. If there's too much load transfer at the rear, the car tends to oversteer during cornering because the rear tires cannot provide enough grip for the rear end to follow the front of the car. This is why the anti-roll bars and the spring rates are very important in this case, because they are not magically creating the grip, but they are actually adjusting the load transfer across the axles and moving the compromise between front and rear axles. This is the part that makes load transfer matter. If a tire carries more vertical load, it can usually generate more force. So at first it sounds like the load transfer should be good, right? More load on the outside tire, the more grip it should give you. But the tires are not linear. So if you double the vertical load on a tire, it usually does not double the force that it can generate. So when the load moves on the outside tire, it is gaining force. At certain point, it starts to drop in coefficient of friction, and at the same time, the inside tire has been unloaded, so it's already producing less load than it usually would. And because the outside tire's gain is much smaller in comparison to the inside tire's loss, the overall grip that the axle can produce reduces significantly. And that is the tire load sensitivity, which is the exact reason why the load transfer is usually bad for maximum grip. But it could sometimes be useful for the balance and control of the vehicle. This is where the trail braking comes into the picture because it changes the balance of available tire forces. Different tires remain more heavily loaded as the steering input is introduced, while the rear tires are unloaded and they have less lateral grip available. The result of this is more forward biased lateral force, which helps the car rotate by developing some yaw moment. If overdone, the rear can become very unstable, or the front tires can become too saturated because of the combined braking and cornering. Throttle generally shifts the balance rearward. As the car accelerates, the load transfers away from the front tires and onto the rear tires, and this can help particularly in the rear wheel drive cars to put on the traction on the road during the corner exit. However, if the front tires are unloaded too quickly whilst there's still steering demand left, their available lateral force reduces and the car runs wide into the understeer. So that's load transfer. It is not a mysterious racing phrase for you anymore. It is the car that is constantly redistributing its vertical loads on all four of its tires. And this is exactly why the setup engineers care more about keeping the CG height as low as possible, making sure the anti-roll bars, the roll stiffness, the suspension properties are fine-tuned so that the load transfer is as minimum and as efficient as possible, so that all four of the tires get evenly distributed loads so that they can produce maximum amount of grip when the car needs it the most. And this is also why a good driver will carefully modulate his inputs while braking, while turning, and while accelerating so that the loads are evenly distributed across four tires, which is giving him maximum control over the car, and the car handles really good for him.